All right. Now let's talk about softmax classifiers. Softmax classifiers are sometimes called multinomial logistic regression. And some of you might be wondering what logistic regression is, and I'm going to talk about what logistic regression is in the following slides. I mentioned this in the previous videos that we want to sometimes interpret the raw classifier scores or the output of the linear classifiers as probability distributions. As you can see here, although these numbers are not exactly probability distributions, we can turn these numbers into probability distributions. And it somewhat looks like probability distributions. And we want to decrease the distance between the model output or the predicted probability distribution and the ideal or ground truth probability distribution. We want to decrease distance between these two probability distributions. And to measure the distance between two probability distributions, we use a metric called KL divergence. And as we proceed to train this model, what we want to do is reduce the distance between these two probability distributions like this. And in this case, the KL divergence between these two distributions is very small. In this case, the distance is quite large, and this is the beginning of training. And softmax helps us doing this. And softmax function looks like this, and this one does not look intuitive. And I'm going to give you a concrete example here. First of all, probabilities must be larger than or equal to 0. And here we have some minus numbers. And to do so, to achieve this goal, we are going to exponentiate all these three numbers. If you have other classes like ship or airplane like this, like some number like 3.7 minus 2.5, we are going to exponentiate these numbers as well if we have other classes like this. And after this process, all the numbers become positive. And we say these numbers are unnormalized probabilities, because probabilities must sum to 1. However, these numbers do not sum to 1. Therefore, we call these numbers unnormalized probabilities. And how do we normalize these numbers? We get the total sum, and let's say the total sum is S, and divide all these numbers by this total sum. Then we can get normalized numbers. And because we divide all these numbers with the total sum, the sum of all these numbers become 1, meaning these numbers constitute a probability distribution. So now we can understand this part. What we are doing is exponentiate each score and get the total sum like this. And this is the total sum. And we divide each exponentiated number with this total sum. This is the result of this example. So this becomes 0.13, this becomes 0.87, this one becomes 0. Okay, so this is softmax function. And sometimes we call these original numbers as unnormalized log probabilities or logits. You need to get used to this terminology. And how do we calculate the loss with softmax function? We do not care about other numbers. What we want to do is maximize the probability of the ground truth label. And how do we calculate the loss? We take minus log to the probability of the ground truth class, which is 0.13. That's just what we do. And we do not care about the scores of other numbers. Because if this number is not 1, that means this classifier is confused. So we want to reduce other probabilities, but maximize this probability of the ground truth label. And this is something called maximum likelihood estimation. And I'm going to give you the detailed example of what maximum likelihood estimation is in the following slides. And as I told you, what we want to do is, this is the current predicted probability distribution. However, the correct probability distribution or ideal probability distribution is 1 for the ground truth class and 0s for other classes. And we want to make this probability distribution into this ideal probability distribution. Therefore, we ignore these parts because there are 0s here. We only care about this probability. And I told you in the previous slides that to measure the distance between two probability distributions, we use KL divergence, and it is defined as Kullback-Leibler divergence, the developer of this concept. And you can calculate the distance with this equation. And we are using this KL divergence and we could derive this loss function. Okay, so here, what we are doing is we just want to maximize the probability of correct classes. Now you can understand this equation. So for given input X, this is given input, and this is the probability of the correct class, and we want to maximize the probability of the correct class. And putting it all together, how do we calculate this probability? We get the total sum and just extract the probability of the correct class. Here, I'm going to give you 2 questions. First question is, what is the minimum and maximum possible softmax loss? And the second question is, at initialization, all Sj will be approximately equal. Because in the beginning of the training process, our classifier does not have any knowledge. So it will say, I'm not sure. Without any training, it will say cat, 1/3 car, 1/3 frog, 1/3. I'm not sure. That's what our classifier is going to do in the beginning of the training process. So that is what this question 2 is about. And if that is the case, what is the softmax loss, assuming we have C classes? Think about these problems or questions on your own, and then move on to the next part. All right, have you thought about these two problems? The minimum possible value is of course 0. If the probability of the correct class is 1, then log 1 is 0. So the minimum possible value is 0. And what if we put 0 here? Then it could go infinity. Okay. Second question, at initialization, all Sj will be approximately equal. What is the softmax loss assuming C classes? It's going to be log C. Because I already told you that if you have C classes like 1, 2, 3, 4, and C class, and in the beginning, at the beginning of training process, all the probabilities will be predicted as one seed like this. Uniform distribution. And let's say this one is the correct class. And how do you calculate the loss? Minus log 1 seed. And that becomes log C. And why do we care about this kind of situation? Because when we first implement our softmax function, we need to debug or check whether our implementation is correct or not. And to check whether our implementation is correct or not, we put these numbers and compare the output of the function. Okay, let's compare softmax and SVM. The first process is the same. We just do matrix multiplication and add bias to the input. So the input image becomes flattened and then multiply with the matrices. And this line and this line, and each line respectively represents each class template. And then we sum all these numbers and we get these 4 vectors. And hinge loss or SVM loss, these two represent the same concept. We can calculate SVM loss right away from this square vector. And we saw this. And in the case of softmax or cross entropy loss, we need to do some extra jobs. We first need to exponentiate this vector and then normalize this vector to make this a probability distribution. And we do not care about other classes, but only the ground truth class label. And here, yi is represented as 2, meaning that 0, first, second, this one is the probability of the correct class. Okay. And this was the equation of softmax and this SVM. And assume scores are like this, and the ground truth label is 0. And what is the softmax loss and the SVM loss? You know how to calculate this, right? And if we double the correct class score from 10 to 20, what happens? Think about it on your own. Okay, what is going to happen? In the case of SVM, nothing much. However, because in the case of SVM, if the margin +1 is acquired, then adding more scores to the correct class does not change the loss. However, in the case of softmax, it changes sensitively because softmax is not satisfied at all until the probability of the correct class becomes 1. And this is very hard to achieve. Therefore, softmax function becomes rarely 0. However, we can make SVM loss 0 quite easily than softmax. Okay, that was about softmax function. And let's implement this together. Okay, implementing softmax is quite straightforward. I'm going to give you a test case. Let's say X looks like this, an array of numbers. And if we put this number into our softmax, then the output is going to be this array. Oops. And implementing softmax is quite easy. What we need to do first, we first need to exponentiate the input vector. And that is easily achievable by calling np.x like this. And to normalize, we need to get the total sum by calling np_sum like this. And we just divide the exponentiated vector with the total sum and return this number. That's all.